Welcome back to Deep Learning, and we want to continue our analysis of regularization methods. And today I want to talk about classical techniques.
The field is kind of stabilized to the point where some core ideas from the 1980s are still used today.
And that was my 1987 diploma thesis, which was all about that.
So here is a typical example on a loss curve over the iterations on the training set. And what I show here on the right-hand side is the loss curve on the test set. And you see that although the training loss goes down, the test loss goes up. So at some point, the training data set is overfitted and it doesn't produce a model that is representative for the data anymore. By the way, always keep in mind that the test set must never be used for training. If you trained on your test set, then you will get very good results, but it's very likely to be a complete overestimate of the performance. So there's the typical situation that somebody runs into my office and says, yes, I have 99% recognition rate. And the first thing that somebody in pattern recognition or machine learning does when he reads 99% recognition rate, did you train on your test data? This is the very first thing you make sure that has not happened. And then you did some stupid mistake, there's some data set pointer that was not pointing to the right data set, and suddenly your recognition rate breaks in. So be careful. If you have very good results, always scrutinize that they are really appropriate and that they're really general. So we have to be very careful about this.
Because it doesn't work.
So instead, if you want to produce curves like the ones that I'm showing here, you may want to use a validation set that you take off the training data set you never use in training, but you can use it to get an estimate for your model overfitting. So if you do that, then we can already use the first trick. We use the validation set. We observe at what point we have the minimum error in the validation set. And if we're at this point, we can use that as a stopping criterion and use that model for our test evaluation. So that's very typical to use the parameters with the minimum validation loss. Another very useful technique is data augmentation. So the idea here is to artificially enlarge the data set. Now you ask, but how? Well, the idea is that there are transformations on the label which should be invariant. Let's say you have the image of a cat and you rotate it by 90 degrees, it still shows a cat. Obviously, those augmentation techniques have to be done carefully. So in the right-hand example, you can see that a rotation by 180 degrees is probably not a good way of augmenting because it may switch the label. So there's very common transformations here, random spatial transforms like affine or elastic transforms. Then there's pixel transforms like changing the resolution, changing noise, or changing pixel distributions like color, brightness, and so on. So these are typical augmentation techniques in image processing. What else? We can regularize in the loss function. And here we can see that this essentially leads to maximum a posteriori estimation. We can do this in a Bayesian approach, where we want to consider the uncertain weights W and that they follow some prior distribution W. And now if we have some data set X with some associated labels Y, we can see that the joint probability is the probability of W given X and Y times the probability of X and Y. We can reformulate that into the probability of Y given X and W times the probability of XW. And from these equalities, we can derive the Bayes theorem that the conditional probability for W given Y and X can be expressed as the probability of Y given X and W times the probability of X and W, and this is divided by the probability of Y and X. So this we can rearrange a bit further, and here you see that then the probability of X, the probability of Y pop up. You can even take out the probability, and this then cancels out, which then finally yields the following map estimate. So we can actually seek to maximize the joint probability as maximizing the conditional probability of y given x and w times the probability of w. So typically we solve them as maximum likelihood estimators, the left-hand side problem, times the prior on w, which is the right-hand side problem. So we essentially can say this is a maximum likelihood estimator, but we augment it with some additional prior information. And here the prior information is that we have some knowledge about the distribution of w. For example, w could be sparse, or we could draw some other source of knowledge where we learn something about w. In image processing, what is used very often is, for example, that natural images are sparse with respect to their gradients. So there's all kinds of sparsities that can be employed by such a prior in typical image processing problems. Now the interesting part is that this map estimator can be reformulated, and if you attended pattern recognition, you know what I'm talking about. We've seen that the maximization of the maximum likelihood estimates results in the typical loss functions that we're talking about. Now if you start with the map estimate, you essentially end up with a very similar estimate, but the shape of the loss function is slightly changed. So we get a new loss function L tilde. It's like the L2 loss or the cross entropy loss, plus some lambda and some constraint on the weights. So here we enforce minimum norm, minimum L2 norm. Now with a positive lambda, we can identify this, by the way, as the Lagrangian function of minimizing the loss function subject to, so with constraint, norm of w smaller than alpha with some unknown data-dependent alpha. So this is exactly the same formulation. Furthermore, we can now bring this into the backpropagation of the augmented loss. And how this is typically implemented is you follow the loss of the gradient. So this is the right-hand part of the loss. This is what we already computed with the learning rate eta. And then in addition, you apply this kind of shrinkage. So the shrinkage step here can be used in order to implement the additional L2 regularization as approached above. So the nice thing is now that we can simply compute the backpropagation as we used to do it, and then in addition use the shrinkage in the weight update. So we also get very simple weight updates and that allow us to involve those regularizers. If we choose different regularizers, the shrinkage functions change. So if we would optimize the training loss now for lambda, we would usually receive lambda equals to 0, because every time we introduce a regularization, we are doing something that is not optimal with respect to our training loss. But of course we introduce it because we want to reduce the overfitting. So this is something that we cannot observe directly in our training data, but we want to get better properties on an unseen test set. This will even increase the loss value of our training data set. So be careful with that. So again, we increase the bias for reduced variance. Here we have a visualization of the effect of different regularizers. So here, for example, the L2 loss, the unregularized loss would of course result in the center of the ellipsis in red. But now you do the additional regularization, which enforces your W to be small, which means that the farther you are away from the origin, the higher your L2 loss will be. So the L2 loss pulls you away from the data optimal loss with respect to your training data set, but hopefully it describes some prior knowledge that we haven't seen this way in the training data set, which will then result in a model which is simply better suited for the unseen test data set. We can also use other norms, for example, the L1 norm. So here we then again end up in a Lagrangian formulation where we have the original loss function subject to the L1 norm being smaller then some value alpha with an unknown data-dependent alpha. And here then we simply get a different shrinkage operation, which now involves the use of the sine function. So this is again an implication of the subgradient. So here a different way of shrinkage has to be employed in order to make this optimization feasible. But again, we used exactly the same gradient for the loss function as we used previously. So only the shrinkage is exchanged. Now we can also visualize this in our small graph. The shape of the L1 norm is of course different. With L2 we had this circle, and with the L1 norm we get this essentially diamond looking shape. And now you can see that the minima that are selected are likely to be located on the coordinate axis. So if you try to find the minimum position of this L1 norm and the unregularized loss, you will see that the point of minimum unregularized loss intersected with this W1 loss is essentially on the y-axis in this plot. And this is a solution that is very sparse, meaning that we only have entries for y in our weight vector, and the entry for x is very close to 0 or equals to 0 in this case. So if you want weights, or if you want to create networks with few connections, you may want to introduce an additional L1 regularization on the weights. This will cause sparse weights. What else? There's also more norm constraints. For example, we can set a limit on the norm of the weights. And here we just enforce them to be below a certain maximum. We want to have the magnitude of W to be below alpha, where alpha is a positive constant. And if you do so, then we essentially have to project onto the unit ball with every parameter update. And this is again a kind of shrinkage, which essentially prohibits exploding gradients. But be careful, it may also simply hide them, such that you don't see them anymore. There's many other variants of changing the loss. You can have a constraint and an individual lambda for every layer. So you could constrain every layer differently, but we haven't seen any gains reported in literature.
Engineers and companies and labs and grad students will continue to tune architectures and explore all kinds of tweaks to make the current state of the art slightly better. But I don't think that's going to be nearly enough.
Instead of the weights, also the activations can be constrained. And then this leads to different variants. For example, in the sparse autoencoders, we will talk about this. There we're not regularizing the weight, but we are regularizing the activations to form a specific distribution or to have sparse activations, which is also a very interesting problem. And we will talk about this a bit more when we talk about autoencoders and unsupervised learning.
But it's all going to happen. I mean, we are going to get to human level intelligence.
So next time in deep learning, we want to continue to talk about regularization methods, and we'll look into the very typical ones that we are also seeing particularly made for deep learning. So very interesting approaches that are slightly different from what you have seen in this video. So thank you very much for watching, and goodbye.